Okay, so following on the heels of resonance forms and resonance structures, um, sometimes molecules will have multiple resonance forms, but some of them are more stable than others. And so often we want to assign or rank the stability of different resonance forms. This is especially true when you have molecules that aren't symmetric. So what we've done so far are a bunch of symmetric resonance molecules. So we did, you know, ozone that had a nice symmetric structure. We did nitrate, which had a nice symmetric structure. But what happens when we have other structures that can still have resonance but aren't symmetric, in which case we don't have a simple average of all of those forms to produce the actual experimental form. In that case, we need a sort of new accounting tool that's really straightforward, that just accounts for this idea called formal charges. Formal charges are a mechanism to count up how many electrons are actually being shared or existing on any one atom. And we'll have some general sort of advice as to how we use formal charge to rank the stability. So the definition, the sort of mathematical definition of formal charge is just to count up how many valence electrons should be on the atom, just doing what we already know how to do. Look at the periodic table, look where it is, what group it is, and then figure out how many valence electrons there are. And then we subtract how many bonding electrons it has, but we divide that by 2 because these are shared. So we just want to account for this for each atom, how many valence electrons it should have, subtract how many are being shared in the bond, and then subtract how many lone pairs or non-bonding electrons we have. And a sort of perfect formal charge would be 0, because we'd be using up all the valence electrons to make bonds or as lone pairs. If we have more or less than the number of valence electrons that we originally have being used in bonding or non-bonding, then we'll end up with a formal charge that's non-zero, and that can be net destabilizing for that resonance form. So we'll walk through some examples to highlight how to think about this formally. So let's do this with the example that we've already done before. This is the NH4 plus polyatomic ion, or ammonium. We already drew this structure before, so I won't go through that in detail. You can look back to a previous video. But let's think about invoking this new sort of idea of formal charges on a molecule that we've drawn before. So we want to account for a formal charge on each one of these atoms within the overall structure. So let's do this first, say, for hydrogen. So for the hydrogen atom, to compute the formal charge on each, we're going to take the number of valence electrons that the hydrogen atom should have, which would be 1. So I'm just going to write Fc here for formal charge. That would be 1, which would equate to the number of valence electrons in the atom. And then I'm going to subtract 1/2 times how many bonding electrons there are. So each of these hydrogens, I'm thinking about the formal charge for each. So I'm thinking about just this one to start with. There's 2 electrons that form that one covalent bond. So I'm going to fill in 2 here. And then I'm going to subtract how many non-bonding electrons it has. And it turns out hydrogen doesn't have any. And so I'll subtract 0. This will give me a formal charge of 1 minus 1/2 times 2. So 1 minus 1 minus 0 is 0. So the formal charge, we'll do this in green, on this hydrogen would be 0, but since all these hydrogens are the same in this compound at least, all of these would have a formal charge of 0. Okay, so let's do the same thing then for our nitrogen atom. So the formal charge in this case is going to be how many, again, how many valence electrons does the nitrogen have to start with? That's always going to be 5 based on it's a group 5A atom. We're going to subtract 1/2 times all the bonding electrons that it has. So this is a little bit different. It's the central atom, so it's got 2, 4, 6, 8 that form this bond. So all 8 of those. And then we're going to subtract any non-bonding electrons, in this case 0 again. So this will be 5 minus 1/2 times 8 would be 4, which would give us a formal charge of 1. So I'll put a +1 on that nitrogen. So in this case, and actually in every case, the formal charges are really just an accounting mechanism for where are the electrons actually located in this molecule. Are they more on the nitrogen, or are they less on the nitrogen, based on whether this is a positive number or a negative number? More positive formal charges mean it's electron deficient. More negative formal charges means it's electron rich. Some molecule or some atoms are good at being electron rich, others are not. And so we'll talk about how this impacts the stability. But one takeaway here is that the sum of all the formal charges on a particular molecule will always add up to whatever the charge of that molecule is. In this case, if you add these up, we get 1, which is the same as the charge on that polyatomic. If you have a neutral molecule, then all of your formal charges should add up to 0. If they don't, then you might have made a mistake somewhere in your accounting. So formal charges, as I mentioned before, are really useful for evaluating or assessing the stability of resonance forms, especially for non-symmetric molecules where all the resonance forms aren't identical. And the general set of criteria that we employ, so we start by taking a molecule, just like we did for ammonium a few seconds ago, and we assign all the formal charges first, and then we use this set of 3 criteria to evaluate stability of the individual resonance forms. So the first step is that overall, a resonance form that has smaller formal charges is going to be preferred. You don't want a bunch of really highly charged or formal charges on individual atoms within a molecule, because that means that you have atoms that are either very electron rich or very electron deficient, which increases the reactivity of that particular molecule, which is sort of inversely related to its stability. So lower formal charges overall on individual atoms is better. Second criteria is that if you have negative formal charges on atoms in a molecule, it's better if they're on the most electronegative atoms. And that should make sense because we know electronegativity is the desire for an atom to have electrons near it. And so it makes sense that if you have an electron-rich atom in a molecule, that's one of your most electronegative atoms. The third criterion is that if you have multiple atoms in your molecule, each of which having a formal charge that's non-zero, you'd prefer not to have 2 charges that are the same immediately adjacent to each other on atoms. So positive of a positive or a negative in a negative. You'd rather have these separated or have a positive and negative adjacent to each other. So let's put these criteria to practice on this example of N2O gas, which is down here in purple. So I've got 3 different resonance forms for the N2O molecule here. I won't walk you through those, but they're all equivalent resonance forms. And what we want to do to start is just to count up the formal charges on each of the atoms. And so remember, the formal charge is going to be equal to whatever the number of valence electrons are on that atom minus half of the bonding electrons minus all of the lone pair electrons. So we'll start with this nitrogen on the far left, and we'll say it has 5 valence. It should have 5 valence. And then we're going to subtract half of the 6 of the triple bond here, meaning 3. So 5 minus 3 minus 2 makes this a 0 formal charge. Nitrogen here again has 5 minus 4 for the half of the bonding electrons, and there's no non-bonding lone pair electrons, so this is a positive 1. Oxygen should have 6, so we have oxygen minus the 1 coming from this makes 5, minus the 6 lone pairs makes minus 1. We can double check our math and make sure that this is a neutral molecule, so the formal charges should add up to 0. So 0 plus 1 minus 1, that's 0, so that's all good. We assigned those correctly. Let's do the same for all of these. Take a pause, make sure you do this yourself. When you unpause, I'll have this worked for you. Alright, so I've got the other 2 compounds here with their formal charges associated with them. Make sure you take the time to validate that yourself. So let's apply these 3 criteria to assess the relative stabilities of each of these. So first is smaller formal charges are preferred. So let's look, and we can look at this first one. We've got a 0, a +1, and a -1. Over here we've got a 0, a +1, and a -1. So just looking at this first criterion, these two resonance forms are equivalent to each other in energy. But if we look over here, this has got a -2, higher formal charge. So we'd say that this intrinsically is calling out to say that this is going to be the least of the stable. So I'm going to write 3 here as the least stable, just simply because you've got a really electron-enriched nitrogen here. That's not good for the stability of that overall structure. Okay, so now we need to assign or look at these other two. So 2 says the most negative formal charge should be on the most electronegative atom. So over here we've got oxygen with the negative, and here we have nitrogen. If you look at the periodic table, oxygen is in group 6A, nitrogen is group 5A. That's further to the right, meaning it's more electronegative. So this would be actually a more stable structure based on this criterion. Let's evaluate both based on 3 just in case. Like charges should not be adjacent. In either structure, we only have opposite charges adjacent, so both of these are fine according to criterion 3. So it's really criterion 2 that sets these two apart, and it says that this would be the most stable and this would be the second most stable. We could also, just for kicks, look at this like charges should not be adjacent on what we'd already assigned as number 3, the least stable. These we also have 2 positive charges adjacent to each other, in addition to the fact that this is a -2. So this is really, really not stable. So 1 is going to be more stable than 2, and 2 is going to be quite a bit more stable than 3. And so what do we get from this? Well, we know that resonance is just a model. That's not a true reflection of experiment. Experimentally, we would only have one structure that we would measure, not all 3 of these, and it would be some hybrid of all of them. So the true resonance structure that we would get, or the true experimental, we'll just call this experimental structure, that we would measure would be more or most like this first structure. It would have some components of this structure, and it wouldn't really have much component or character contribution from the third resonance form.